Everyone, June the 14th. All right, on the road. On the road. Let's do this. Maximum level of a binary tree. Given the root, the level is 1, the level of children is 2, return the smallest integer x. That the sum of all the values of nodes at level x is maximum. So this will be this one, right? Level 1. This level 1 is level 2. Okay, what do you think? BFS. Are we hitting BFS stuff today? Not sure, but this one is BFS. All right, let's BFS this. Res is equal to, we also need to have the max sum. So res equals 0. Actually, it doesn't really matter. Res should be 1, and max sum shall be 0. Yeah. Oh no. Minus math.inf. Okay. And then we do q equals root. And steps level equals 1. Right? And we say, actually, let's do level 0. While q temp for node in q. Actually, no, I'll do 1. So we can say current sum, right? Or in q, current sum plus equal to node.val. If node.left, temp.append node.left, node.right, temp.append node.right, right? So we go through everything and then we say if max sum is smaller than current sum. What if it's the same on the smallest? Yes, if it's smaller than current sum, then res shall equal to level. That is right. And max sum shall equal to current sum. Once we do q equal to temp and level plus equal 1. So when we got the first one, right, that'll be good. And then we hit the last one, that shall do. And then we return res. All right, give me a shot. Wait, yeah, give me a shot. Is this right? Looks okay. And we need to try an edge case. That's an edge case, single node. Looks fine. 2019. That's a long time ago. .1161 BFS. Okay, that shall do. Why did you torture yourself, right? All right, so next one we go back to the same problem as yesterday. All right, so this is so-called sweep line, DP and sweep line. Many of the top discussions are completely wrong or have incorrect time complexity. Okay. We'll solve it like this. DP, use previous computed results to find the shortest path to RC. Okay, then the answer is yes. In order to find the shortest path, I need to find the best cell to the left, which is just the smallest, right? On the same row as well as the best cell above me in the same column. I agree. Then we take the minimum of these. Since we only depend on cells to the left and above us, we already have the information about them since we're solving from left to right and top to bottom. Exactly. Let dx equals this. Notice that each cell represents a horizontal interval of columns. Similarly, a horizontal interval of rows. Exactly. We can use sweep line with a balanced BST to find at each position what is the best we can do with the current active intervals. Oh, this is a sorted list. Query for minimum maximum key. So it's the same. Even if it's not the same, this is just sorted list, so nothing special. All right, I think we can call an end to this problem. We have the sorted list, right? This is the sorted list solution, which is, quite smart in itself, but I think I also hit a little bit hiccup here as well. Yeah, you have to do a list and then you remove. But the real smart one is the DSU. The DSU is a real smart one. Anyway, so we hit all this, we can call it and go back to problems. Nope. There we go. What is this? Is this the... This is the JavaScript stuff. Nah, I don't want to do the JavaScript stuff. I think these are all JavaScript, right? Wait, this must be counter. TypeScript, JavaScript. Nah, not a fan. No, this is the... Holy crap, they're all JavaScript stuff. Are they all JavaScript? Oh my. Is this one JavaScript as well? Yes. I guess these are all JavaScript stuff. How do I know which one is and which one is not? This, hold on. These seem to be Java. These, is this a JavaScript as well? Nope, this is not. I think these are, this probably is JavaScript. No, crap. All right, I'm really confused. I'm really confused which one is and which one is not. Debounce, this is definitely JavaScript. Function composition, this is JavaScript. Memorize JavaScript, yes. This must be, this looks like JavaScript. Yep, so we skip. Promise is definitely JavaScript. But I think starting from here, these look not JavaScript. All right, let's do this. Find the width of columns. Of a grid given a zero indexed MN integer matrix. The width of a column is the max length of its integers. The width of a column is the max length of its integers. For example, if this, the width of the only column is 3, since minus 10 is of... Wait, hold on a second. What does it mean? The width of a column. Oh, a column. This is considered a row. Wait, hold on. Is this a column? What is a column? Is the maximum length of its integers. Oh, the width of a column. So this is one column, it has 3. The width of the column is 3, since minus 10 is of length 3. Return an integer array of size n, where answer I is the width of the ith column. The length of... Oh no, here we go. The length of an integer x with len digits is equal to len if x is non-negative and len plus 1. Oh, the length of its integer. So this is the length 3 because I have 3 characters. So that is the width of the column. So in here, the width of the column is going to be 333. Right? The first column is 3, second column is 1, the third column is 2. Now I see. Okay, well, we can do O(n squared, sure. Is there any easier way to do that? I mean, we can just go through everything and update. You do have to go through everything and then we update. Yeah, that shall do. This is number 2639. 2639. All right, so we're gonna do here. We are going to say res is equal to, let's do m and line grid 0, right? And then we can do 0 times n, right? Because that's so many columns. And then we just say for row in grid and for v in row, and we need an I, and we can enumerate the row, and then we say res I shall equal to maximum res I, and then str v, and then we need its length, and then we return res. That, my friend, shall do. Put it here, get these running. Looks solid. Yeah, it runs so slow though. I don't know, do you think it's a better way? I don't think so. You have to go through every single one. One line solution. I mean, can you do a one line? Yes. Technically, yes. You just iterate through the columns, right? Yeah, so I'll say something like this. Okay, something like this. We can say top level is going to be for j in range len grid 0. Okay, and then for I in range len grid, right? And then we go through everything, then we just say it's going to be the maximum of, you know what, that's not right. I think it shall be here, maximum of len str something grid ij. Okay, grid ij for this len of this, maximum of this, then for j in len this. So we shall return a list of this thing. Does that make sense? Oh, I don't have O. That should be 0. Yep. And this one works. That's just for fun. Nothing really special. I see, do we have the same? Ah, dear God. Use this one again. Zip. Yes. I've seen this trick before. You zip when you first like destruct the array of array, and then you zip it. Then what you get is a iterator for every single column, and then you just handle this column. Zip. Yeah, I forgot about zip. Find the score of all prefixes of an array. We define a conversion array of an array as follows. Conversion convert I equals array I plus maximum array 0 to I is the maximum value of, okay. We also define the score of an array as a sum of the values of the conversion array of array given a 0 indexed integer array. Return an answer of length I with answer I is the score of the prefix. Hold on, let me read this again. So we have to convert, I know, is the current plus the maximum of everything before it. And the score array is the sum of the values of the conversion. Okay, it's the sum of the conversion. And then given a 0 indexed integer array of the length, return an array answer of length n, where answer I is the score of the prefix. Man, I need a piece of paper and hold on, I have paper. Paper or pen? Alright, let's take a look on this thing. What do we have? 2, 3, 7, 5, and 10. Okay. So if we want to say, so we need to first get a convert. 2 is just 2. No, 2 is actually 4, right? Because it has to be, that'd be 2 plus 2. And then 3 plus 3, 7 plus 7, 5 plus 7, 10 plus 10. All right, so convert is 4, 6, 14, 12, and 20. And then we're going to compute the score. The score of an array is the sum of the values. So the score is just the prefix sum of convert. All right, 24, 36, and 56. Exactly. So now we know the step from convert to score. All we need to figure out is how to get convert, right? So we just need to think how to get convert. Now convert, we have to add everything there. So that one is done. So the next thing we need to do is to find the maximum value. And the maximum value can be found as you iterate through. So this problem is basically solved. maybe what we can even do is to get the score in one shot, okay? Because at every position, you already know the value. And the next one, you know the value, just add to it. Yes, we can get this in one shot, you know, one pass. This is not really a, you know, like a tough question. It's not, it's a little bit, I mean, I feel like they came up with this problem, you know, back to front. I don't know if you know what I mean. It's just, you know, back to front. Okay, so we have a pre-max. Okay, so what's the maximum value? What's the minimum value? Minimum value is 1, so pre-max can be 0, right? So what we can do is res equal to this. Okay, for n in nums, right? Then we say, we probably want to do this, right? And then we say res dot append, okay? Pre-max, maximum, current max. Now we should do pre-max equals the maximum of pre-max and n. And this shall append res minus 1 plus pre-max plus n. And then we'll go to the next one, and then we'll return res. I think this shall do. Let's give this a shot. Of course, I forgot. Let's only return this. I don't know. What do you think of doing the 0 thing? It's basically just to make this one easier. That's all why I do it. I think this shall do. Yep, this one will do. Just a prefix sum. Just a fancy way to produce prefix sum. Okay, prefix sum. And you can do that. Dear God, accumulate. Zip. That's interesting. Oh, holy crap. This is, oh yes. Oh my. Yep, this one produced the prefix, not sum, but prefix max. Okay, this is prefix max. And then you zip this, then you add them together. Oh, actually, I shouldn't upload him. I should upload him. Very interesting idea. Let's do this again using this to accumulate, right? To accumulate to solve the problem in one line. I kind of feel this can be solved in one line. I need to give credit. I'm not gonna give credit to him. I'll give credit to this guy. Or girl. All right, so we're gonna return, right? So we're gonna do accumulate nums and use a max, right? And then we're gonna zip nums and this, right? And then we say for n max pre-max in this, then we're just gonna do n plus pre-max, and then we'll list and accumulate whatever is this thing. Dude, this is so good, so smart. Nice. Good solution. Okay, so that's that. We'll move on to the next one. Cousins in binary tree. Number 2. Given the root of a binary tree, replace the value of each node in the tree with the sum of all its cousins' values. The value of each node in the tree with the sum of all its cousins. 2 nodes of a binary tree are cousins if they have the same depth with different parents. Return the root of the modified tree. The depth of the node is the number of edges in the path from the root node to it. So, for example, in this one, holy crap! Replace the value, so replace this with the sum of its cousins. So this one doesn't have any cousin. And this doesn't have any cousin. Oh my god. And this one has a cousin. This one has a cousin. And this one has... Ooh, interesting problem. Alright, so... what do you think? Well, I mean, it's everybody on the same line, right? Because it has to be on the same level. 2 nodes of our cousin if they have the same depth, right? So it has to be on the same level. And on the same level, we need to identify who's whom, right? Who's whom. We can use a... holy crap. We can use something. Let's say, and it's a binary tree, right? It's a binary tree. The sum of all the cousins. I can produce the sum of the entire level, right? And we also know the sum of my siblings. So the sum of my cousins is the total sum of a level minus the sum of me and my siblings. Right? Yeah. So what we need to do is BFS. And as we BFS for each row, for each row, we'll find out, okay? We'll find out the total sum and the sum of each. Then we have to do it twice. I kind of don't want to do it twice. No, I don't think you need to do it twice, because as you're going through the current row, you are appending to the next row. So when you're appending the next row, you can already compute the total sum of the next row, right? And then you save it. And then when you get to the next row, you go through the current. Every node, it goes through the current. And then you just need to figure out what. So there is going to be a, can I modify in place? I'm going to modify in place, which I think will be easier to do. Okay, so I have some idea, but we will have to get this ball rolling. Let's get the ball rolling first. I feel if I get the ball rolling, I have a higher chance of really coming up with a solution. All right. So we're going to return root. So we're going to change root. And what we want to do is to know who is the total, okay? So let's get a Q up. So Q shall be root, right? I also need its parent. the parent. I think I can say node is node to check its parent. Or node dot address. I can use node dot address because I need to use the parent node. The parent node has to serve, okay? The parent node has to serve as the key. I am not sure if we can do. Wait, was this say ID something? Okay, I forgot. Okay, I forgot, man. So is that ID? A? Yes, this is going to be our key. So what we're gonna do is its parent. Well, we're gonna say your parent and your node. Okay, and what we also gonna have is what? So you're going through a current, so you should know the sum of your siblings, the sum of the total, right? So we can say this is gonna be a pre. So we're gonna say the total is going to be root.val. I need to start from root.val, right? That's that. And then we need to say -1 is equal. Oh my god. Me god. It's a mixture. Maybe you just keep 2 values. Okay, yeah, let's keep 2 values. It will be easier. Okay, so we get, that's the total. This we can handle, right? And sibling sums, sib sums. Okay, so this one we can do -1 is going to be root.val. Okay, then while q. Perfect. Temp equal to this. For node in Q, actually for parent ID, node in Q. Okay. What do? We need to push the next one in, but at the same time, we also need to have the current total, okay, and current pre-sib sum, okay, pre-sib sum. Current sib sums equal to this. Okay. Now what? Now we need to find the if node.left temp.append node.left, that's fine, and current total plus equal to node.left.val. Right? That's the total. And a current sib sums, which is the ID of your node. This is the parent, plus equal to, yeah, let's go default dict int. Oh, counter. Let's do counter. Nah, default dict will be fine. Let's do default dict. Yeah, default dict will be fine. Default dict int. Right? So this will plus equal to what? Node.left.val. This is the sibling sum, right? So we're done, and we do the same thing for the right. Node.right, right? If node.right, we push it in, we get a total sum, we get a sibling sum. Once we've done all that, then we can say node.val equals, right, the pre-total minus pre-sib sums my parent. So this is everything else. Okay, once it's done, we do blah 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 blah. Once we're done, pre-total equals to current total, pre this equal to current this, and temp equal to q equal to temp, and then blah blah blah. Once we're done, we just return root. We don't create a new one. We change everything in space. I actually don't think that is desired, right? It shouldn't change, but Screw this. If you don't change, you had to create a new one. We can create a new one. But I don't want to create a new one. Let's see if this is correct. Cannot unpack. Oh, for sure, because you append wrong. You need to append two things. Come on. Where is your parent ID? Where is your node? This is your node. Don't forget ID node. Looks solid. Wanna try a single one? Yeah, I can try a single one. Right, not too shabby, but maybe there are better solutions. Okay, we did this in place. I mean, it should not be hard. No, it should not be hard. Well, what we can do is just, if we are not, well, creating new ones, that instead of using passing the queue of this, we're gonna put the actual parent node, so we can produce new things, right? But it is not that much work to create a new tree. Okay, let's take a look. Level sum. Yeah, they return the root, so no hard feelings. Okay, what is this t? T equals sum. I think sum is a level sum. Yes. And then t equals sum. Yes, it's the same. All I did is just not do it twice, right? That's all I did. Okay, that will be it. And we will continue. No, a good thing to do for tomorrow. I have a meeting, conference tomorrow, so yeah, better just read through this tomorrow, so it will help me to stay awake. All right, that will be it. I